Hey everyone, and welcome to today's Explainer. I am absolutely pumped to have you here because today we're decoding the literal language of the digital universe. Think about it. Every single time you power up your computer or save a file to a solid-state drive or really just interact with any digital device, you're relying on this hidden, massive architecture of decision-making. We're talking about Boolean logic. And hey, I know it can sound intimidating, but let's just strip away the mystery right now. We're going to see exactly how simple ones and zeros are manipulated to run literally all the complex tech we rely on every single day. By the end of this explainer, you aren't just going to understand these building blocks, you're going to be ready to build and analyze them yourself to absolutely ace your exams. So, let's get into it.
Here's our game plan for today. We'll kick things off with standard logic gates, learn how to translate different logic formats, see these gates actually in action with a real-world circuit, and then crucially, we'll break down exactly how to score top marks on your exam papers.
All right, so first things first, what actually is a logic gate? At its core, it's just an electronic circuit that takes binary inputs and spits out binary outputs. That's it, just a flow of ones and zeros, ons and offs. But, don't let that simplicity fool you. The device you're watching this on right now, it's made up of thousands upon thousands of these individual logic gates. And when you combine them, they form these incredibly intricate logic circuits that power our entire digital world.
So let's jump right into Section 1, Standard Logic Gates. Time to master the basics.
Okay, we need to get completely fluent in the rules for our first three fundamental gates. And notice how distinctly different they are. Let's look at the NOT gate first. The rule here is super simple. It's a direct inversion. The output is a 1 only if the input, let's just call it input A, is 0. It literally just flips the signal. Next up is the AND gate. Now this one is strict. The output is 1 if and only if both inputs A and B are 1. If even a single input is 0, the whole output is 0. Simple as that. Finally, we have the OR gate. This one's way more accommodating. The output is 1 if either input A is 1 or input B is 1. Or hey, if both are 1. Oh, and before we move on, I really want to highlight a critical rule from our source material here. The NOT gate, that is the absolutely only single input gate we'll be dealing with. For the Igcse level, all the other gates we cover are strictly limited to 2 inputs. Remember that, it's going to save you marks later.
So, let's map those rules to the actual visual symbols you'll be drawing and analyzing. Look at the NOT gate at the top. It's that triangle with a little circle at the tip. That tiny circle? That's your visual cue for inversion. Always look out for it. Then, the AND gate in the middle. It has a flat back and a rounded front, kind of like a capital letter D, which makes it easy to remember. And the OR gate at the bottom has that curved back and a pointed, almost rocket-like front. Now, right alongside those visual symbols, the source provides us with the Boolean algebra notation, and while it might be optional for some parts of Igcse, knowing it is a massive advantage. Check it out. A bar over a letter means not. A little dot between letters, like A dot B, that's your AND operation. And a plus sign, A plus B, is your OR operation. It's basically just a quick, clean mathematical shorthand for those truth tables you see right there in the center.
All right, moving on to our second group of 3 gates, NAND, NOR, and XOR. Honestly, you can just think of NAND and NOR as the rebellious opposite siblings of the AND and OR gates we just talked about. For a NAND gate, which literally stands for not AND, the output is 1 as long as inputs A and B are both not 1. It does the exact opposite of the AND gate. Then for a NOR gate, or not OR, the output is 1 only when neither input A nor input B is 1. So they both absolutely must be 0. And finally, we have the XOR gate, which is short for exclusive OR. This one's very particular. The output is 1 if input A is 1 and B is 0, or if B is 1 and A is 0. It strictly requires one or the other to be on, but never, ever both.
Let's connect those new rules to their symbols. Notice anything familiar about the NAND and NOR gates here? They look exactly like the AND and OR gates from the previous slide, but with one absolute game changer, that tiny circle at the output end. Just like we saw on the NOT gate, that little circle is visually screaming at you that the output is being inverted. And take a look at the XOR gate down at the bottom. It looks a lot like a standard OR gate, right? But it has that distinct double-curved line at the input side. That extra line is your visual reminder of the exclusive rule. And if we quickly glance at the Boolean notation here, NAND is represented by A dot B but with a bar over the whole entire thing showing the AND is inverted. NOR is A plus B with a bar over it.
Moving right along to Section 2, Translating Formats. Let's get fluent in digital logic. Okay, so the real secret to mastering this module is understanding the flow of information. On your exam, you're usually going to be given a real-world problem statement, basically a description written out in plain English. Your mission is to translate that English into a logic expression, which is that mathematical shorthand we just looked at. From there, you map out every single possible scenario using a truth table, which lists all the binary outputs for every combination of inputs. And then finally, you translate that table or expression into a visual logic circuit drawing using our standard symbols. The absolute beauty of this system, you can move in any direction. You might get a circuit and be asked to write the expression, or get a truth table and have to draw the circuit. It's all interconnected like a giant puzzle.
All right, section 3. Let's see what these circuits actually look like in the real world. Let's tackle a real problem statement together. Imagine we have a safety system, and it has 3 inputs, A, B, and C. Here's the rule. An alarm, which we'll call output X, sounds if input A is on and input B is off, or if input B is on and input C is off. So let's immediately translate this plain English into our second format, a logic expression. If we treat on as a 1 and off as a not 1, here's what we get. X equals 1 if, open bracket, A equals 1 and B equals not 1, close bracket. Or, open bracket, B equals 1 and C equals not 1, close bracket. Boom! We've just successfully translated a wordy paragraph into a super clear, logical formula.
Now, let's trace that through the actual circuit at the top. See how the inputs map perfectly to our expression? Let's trace input A and input B. Notice how B goes through a NOT gate first, that little triangle with the circle, because our expression explicitly said B equals not 1. Then A and that newly inverted B flow right into an AND gate together. The exact same logic applies to the bottom half of the circuit for inputs B and C. And finally, the outputs from those 2 AND gates flow into a single OR gate to give us our final alarm output X. Now, please look at the truth table at the bottom. Do you see those 2 columns labeled intermediate values? I cannot stress this enough. This is a massive secret to exam success. Instead of trying to juggle the entire calculation for final output X in your head all at once, this table breaks down the 2 bracketed parts of our expression first. By solving for the left side of the OR statement and then the right side separately, finding that final output for X becomes incredibly simple and, more importantly, totally error-free.
Which brings us perfectly to our final and honestly most crucial section, scoring top exam marks. Let's look at the examiner's playbook.
This is the million-dollar question, right? When the examiner is sitting there grading your paper, looking at your logic circuit drawing or your truth table, what actually separates a perfect score from a heavily penalized low-grade attempt? Well, we actually have direct teacher comments on sample answers from the source material, giving us a literal sneak peek into exactly what they want to see. Let's do a side-by-side comparison. On the left, we've got a high-level, perfect score sample answer for the logic expression X equals A and B, or not B and C. On the right, a low-level answer attempting that exact same problem. Just at a glance, the difference is night and day, isn't it? Look at the truth table on the left. It actually uses those intermediate working columns we just talked about. It calculates A and B first, then not B and C, and then the final output X. It's clean, it's readable, it's complete. Now, look at the right side. The working space is totally blank. The final column is missing values. Like, is that a 0 or a 1 on the 4th row? You can't even tell. And the logic circuit diagram below it? Oh boy, it's an absolute mess. The connecting lines are just crossing over each other aimlessly, making it incredibly confusing for the examiner to follow.
Let's break down exactly what the examiner noted here. The high-level habits that practically guarantee marks are crystal clear. You absolutely must use intermediate working columns. You have to draw clean, unambiguous connecting lines in your circuits. And crucially, you must use the exact standard symbols shown in your syllabus. Now, let's look at the fatal mistakes from that low-level answer. Aside from the messy lines and the skipped steps we saw, the examiner pointed out 2 massive grade-tanking errors. First, the student used a completely non-standard made-up symbol for the OR gate. You can't do that. Second, they drew a 3-input AND gate. Remember that rule I emphasized way back at the beginning? For this syllabus, all gates, except for NOT, are strictly limited to a maximum of 2 inputs. Drawing a 3-input gate just tells the examiner you don't actually know the syllabus constraints.
So let's wrap all of this into the ultimate examiner checklist. If you follow these 6 rules, you are setting yourself up for a perfect score. Ready? First, your marks are strictly awarded for the clear 0s and 1s in that final column of the truth table. To get there safely, Rule 2. Always, always work out bracketed expressions in the intermediate columns first. Third, If you make a mistake and need to change an answer, ensure your alterations to zeros and ones are perfectly clear. Don't just scribble over a 0 and hope it looks like a 1. Fourth, when drawing, only ever use the standard shapes we learned today. Fifth, draw your connecting lines really carefully so the examiner knows exactly which input goes to which gate. And finally, Rule 6. Limit your gates to a maximum of 2 inputs, unless it's a NOT gate, which obviously only has 1. It really is a foolproof system if you just stick to the rules.
We have covered a massive amount of ground today, from learning the basic alphabet of NOT, AND, and OR gates, all the way up to translating real-world safety alarms and totally decoding examiner expectations. So I want to leave you with this one final thought. If the absolute most complex computing systems on Earth, systems that literally route global internet traffic and power massive servers, if they all essentially boil down to simple ones and zeros passing through these standard logical gates, what else in our physical world operates on this exact same binary logic? Once you start seeing the world through the lens of Boolean logic, you realize that incredibly simple, structured rules govern almost all the wild complexity in our modern lives. Thank you so much for joining me for this explainer. Keep practicing those truth tables, keep drawing those ultra-clean circuits, and I will see you next time.